Welcome to P2. Today we are looking at geometric sequences, Unit 5.3. Now, geometric sequence is a little bit different to the arithmetic sequence in that the arithmetic one was to do with essentially what number you add to the next one, so that the difference between each term was always the same, whether you were increasing or decreasing. In a geometric series, or geometric sequence, what you're doing is you're multiplying the previous term by a specific number to get the next term. So if I looked at a sequence like this, say 2, 4, 8, 16, 32, and so on, what I'm doing each time is multiplying by 2. And because I'm multiplying by the same number each time, then this is a geometric sequence. Now, if I end up multiplying by a negative value, so for example, let's do the same kind of thing again, but this time we multiply by negative 2, you can see that what you get is what's called an alternating sequence. Because we are multiplying by negative 2, by a negative value, our sequence is alternating between positive and negative values. And then finally, there's another sequence. Now, if you have a sequence where the value that you're multiplying is between 0 and 1, so for example, let's say we start off with, well, let me give an easy number, 8, and say that I'm going to multiply by a half. Then this one's going to be 4, and then we've got multiplying by a half each time, 2, and then we'll have 1, and then we'll have a half, and then we'll have a quarter, and then we'll have an eighth, and so on. So by multiplying by this type of number, what I get is I get a sequence that is decreasing in size, but that will never actually hit 0. Okay, and obviously if I had a negative value here that I was multiplying, then I would get alternating signs where it's heading towards 0 again, just either side of 0, bouncing back and forth, getting closer and closer to 0, but never actually getting there. Now, let's talk about what we do with this. So what we multiply by, like this one is 2, this one we multiply by negative 2, this we multiply by a half. This is called the common ratio. Okay, so the common ratio, R. Okay, that's the value of what you're multiplying by each time. Okay, what is increasing by or decreasing, if you think of it that way. Now remember from last time, the first term is the letter A. That hasn't changed. Okay, so these are the two things that we're going to be looking at, and then UN is obviously your nth term. So we're going to use these to create our formula for our geometric sequence. So if I think about it in terms of algebra, my first term is A. Then I'm going to multiply by the common ratio, so I'm going to get AR. Then I'm going to multiply that term by the common ratio, so it's going to become AR squared, AR cubed, and so on. So each time I am multiplying by R, the common ratio, as I go up in the sequence. Now you can see the pattern here. So like the first term, R is to the power 0, the second term, R is to the power 1, third term, R is to the power 2, so the nth term is R is to the power n minus 1. And that there is the formula that we're going to be using. Okay, the nth term is A multiplied by R to the power n minus 1. So let's get straight into an example. Find the nth term and 20th term of this sequence. So we've got a geometric sequence, as that's what we're looking at. Often it will tell you in the question, or you can work it out straight away. As there's only two sequences that you deal with, and that's arithmetic and geometric. So if you don't have the same value between each term, then you know it's going to be a geometric sequence. If you had the same value, then it would be arithmetic. So look at how we get from one term to the other. Now, in some cases like this one, it's pretty obvious. We are multiplying by 3. Okay, you can see that. But if it's not obvious and you want to find the ratio, just take one term and divide by the previous term. So if I took the second term and divided by the first term, 6 over 2 is 3. That's then the number that you have to multiply by. Or I could have said take the third term and divide by the second term. 18 divided by 6, 3. Okay, doesn't matter which terms you take as long as you're taking two terms that are consecutive, and then you do in the later term, divided by the previous term. Okay, so that's how you find R. Obviously in this case A is 2, so that's nice and easy. So the nth term is going to be 2 times 3 to the n minus 1. Now we want to also find the 20th term. So it's 2 multiplied by 3 to the power 19, which is going to give me a huge number. So this is a quick and easy example just showing you how to use the nth term of a geometric sequence. Next, I want to look at a different style of question and something that's probably a bit closer to the kind of questions you tend to see more often in exams. The second term in a geometric sequence is 3, and the fifth term is 81. Find the exact value of the eighth term in the sequence. So remember that your nth term is ARN minus 1. So the second term is AR to the 2 minus 1, which is obviously just 1. And the fifth term is AR to the power 4, as it's 5 minus 1. And we know that the second term is 3 and the fifth term is 81. So I've got two equations here. And what we're going to do is equation 2 divided by equation 1. So AR to the power 4 equals 81 divided by AR equals 3. Now, I always do the divide because then my A's will cancel and some of my R's. So you can see here we're left with R cubed on the left-hand side. 3 goes into 81 27 times. So I've got R cubed equals 27, R equals, and the cube root of 27 is 3. Now that I know that, I can actually go ahead and work out A. So let's go equation 1, AR equals 3, 3A equals 3, isn't it? Because R is 3, therefore A must equal 1. Now that we've got that nth term, so UN equals, well, A is 1, so it's just R, which is 3 to the power n minus 1. Finding the eighth term, so U8 equals 3 to the power of 7. And that is 2187. Nice and easy. The third term in a geometric sequence is 16, and the sixth term is 128. What is the first term in the sequence to exceed 1 million? So the first thing, we need to know the nth term. So we know, if I put it down again, and like I've said in previous videos, always write stuff down. The more you write it down, the more you're going to remember it. So we want the third term, which is AR squared, and that is going to be 16. And then we want the sixth term, which is AR to the power 5, and that is 128. So take the bigger one, divide by the smaller one, make our lives easier. AR to the 5 over AR squared, and that equals 128 over 16. So we get the A's cancel in there, R squared with this one's going to give me R cubed. So I get R cubed on the left, 128 divided by 16 is 8, R equals 2. Now I should point out that obviously this one and the one before had an odd power, so it was obvious that this was going to be the same sign, positive. If you've got like a squared or something where it could be plus or minus, then often in the question it'll tell you that the common ratio is positive or the common ratio is negative. Anyway, let's proceed. Now we need to find out A, so let's go to 1, A times 2 squared equals 16. So 4A equals 16, A equals 4. So we've got our nth term is 4 times 2 to the power n minus 1. And we want when the nth term exceeds 1 million. So our nth term is 4 times 2 to the power n minus 1. And of course we want that to exceed 1 million. So the first thing I want to do is divide by this 4. So that's going to be 2 to the power n minus 1 is greater than 250,000. Next thing I want to do is take logs of both sides. And I want to do that to get rid of or deal with my power. So I'm going to take logs of both sides. Now you'll notice I haven't written a base on my log. Most of the time we use log to the base 10, but you can use log to the base e. You can use any log, you'll still get the correct answer as long as you obviously use the same base on both sides, which is what you have to do if you take logs of both sides. Now we can bring this power down. So we're going to have n minus 1 times log 2. And this is, of course, log 250,000. Now I want to divide by log 2. So n minus 1 is greater than log 250,000 divided by log 2. And then all I've got to do is add 1 at the end. So let's actually write this down, n minus 1, and this is 17.9, you can give it a couple more decimal places, 93, and then when I add 1 to it, which I'll just pop over here, we get n is greater than 18.9. So that means it's the 19th term is the one where this is going to first exceed 1 million. So the 19th term is the first term. If you substitute it in to our nth term here, you'll see when you substitute 19 in for n, you get just over 1 million there. And if you substitute 18 in, check the one before, you should get 500 and something thousand. Okay, and that's it. Nothing too difficult about this, hopefully. So what I'll do now is give you a few questions to try, a few easy ones building up to this kind of standard. There isn't much more difficult than this at the moment. And as always, I'll pop the answers at the end of the video.